So, how's everyone doing? I say I muted you all, so I see smiley faces, so I'll take that as
Good.
doing good enough. You're still sticking around, still making it through the semester, haven't given up yet. Good. Okay, so lab 6 is actually kind of a short lab. So I'm going to start by showing you something else, something that I had group meeting with my programmers yesterday, and they're working on adding color combination to Afterglow. And it's still a ways away. And I know it's not really part of this lab sequence, though once it's been developed, we may add one small color combination exercise to lab 1 because students really get excited about it. And it looks like it's going to be really easy. And I know many of you have had students, the enthusiastic ones, who go ahead and attempt this anyway. They collect a red, a green, a blue of something and then go off to some other software like Photoshop or the GIMP to try to combine it. And we just put in a large grant with Tim Spuck to build color combination into Afterglow and do a lot of stuff for blind and visually impaired students, including sonification of color. And I have another small grant out there for building color stuff that I'll know about in about a week or two. But my programmers have just gone ahead and started working. When we can, we work on this kind of grant process where we do all the work in advance, get it all done, then apply, we get the money, and then we have time to work on the next thing in advance, try to get ahead of the grant cycle. And we're fortunately in that zone at the moment. So let me just, I had the group meeting yesterday and I screen captured or recorded a little bit of it. So I'm going to play a recording. Hopefully the audio is good enough. So this will just be 2 minutes of my lead programmer, Josh Hayslip, explaining or demoing the beginnings of this feature. If it comes across that you can't understand the audio, just yell at me and I'll do something.
Okay, so we opened a file that has multiple channels that are part of it. So Afterglow is smart enough now to display this as a single file, which has these different channels. So we can actually open up the individual channels. Some of these channels that are part of this file are table data, which isn't displayed right now, but will be displayed in the future once we support it. But I'll just go ahead and open each of these channels. Into a separate window. So we've opened the red channel, which happens to be the first channel, channel 0, and I happen to know that channel 2 represents the blue channel. Channel 4 is the green.
I'm in a little chat thing.
The last step we can actually do here is we can even select the top level, the entire file, which tells Afterglow that you would like to see all of these channels overlaid and stacked. So we'll double click that to open. And so here are all of those 3 channels stacked together and flattened, but we haven't actually told Afterglow which color each channel should be. So just for ease of looking at it here, we can split the screen to the right. So we have the composite on the right and we have the components on the left. So we'll go ahead and assign the red color map to the channel 0. You can see on the right side, the composite gets updated with that information. And so repeat the process here with channel 2 being blue. And lastly, channel 4 being green. And there you have a color image. And you can always make adjustments to it by coming back to each of your components and adjust the saturation level if you would like a little more red. Or if you want a little less blue, you can go to that one and change it. The image will become a little more green. But each time you make a change on the right side to how your images, your individual channels are modified, it will automatically update it on the right.
Okay. That come through okay? Y'all could see and hear? So I'm pretty excited about that. I don't know if you all are, but yeah, I think probably some of you will be, because this is something that really gets the students excited. If we can make it easy to do within the Afterglow environment, maybe at the end of lab 1, when they're imaging 3 deep sky objects, we'll have them pick one of those to do in RGB as well, and then they can combine it. The danger is they get too excited and burn through all their credits. And right now, the most enthusiastic student in your class may do that, and you can give them more time, but everyone starts burning through their credits, then it's a problem. But I don't know, we'll figure that out when we get there. There's still a tremendous amount to do. We have to be able to export that. Right now, the exports of images are just screenshots, and you'd want to export that in full pixel resolution. We want to introduce things like PSF matching. That was clearly Hubble data, so it looked great. Their data will be shorter exposures, but we've seen what some of these student images look like, and they're not bad. And given this more capable color combination tool, they may look even better than they're coming out. But you know, the 3 images will be taken and may have different blurrings. And so often when you combine RGB, you want to blur the better ones out to match the lesser ones, so the stars are all the same size. Otherwise, you may have like a blue-green star with the red halo around it because it didn't match up well. So there are things we have to do. But what you're seeing there is Hdu files, FITS files. Some of them come with multiple layers called HDUs. I forget what it stands for, but it's like an image, a 3-dimensional data set then. And so what Josh has done is built in the capability to load HDUs. I'll find you here, one of you. There we go. Load HDUs into Afterglow and then treat the layers differently. And some of those layers are table files, and we'll eventually be able to do stuff with them in Afterglow as well. And the radio images that we produce currently outside of Afterglow, they're also HDUs with multiple layers that you can do things with. So this also helps set us up for radio imaging in Afterglow. Anyway, that's that. Still a ways off, but maybe over the timescale of the next year, well, over the next couple weeks, we will release the basics. So this is another tangent. You're all using the version of Afterglow that we released this summer. You all know about the version on Sparge that has debugged many of the issues. So if you run into a problem, try it on Sparge. But we haven't pushed the Sparge version yet. I think Josh wants to get this basic HDU, basic color stuff in the Sparge version before pushing it out to the main server. So some basic color capability should be coming within weeks, but the kind of the fuller version that you need to do more will be later. Okay. Let's see. So
yeah, Dan,
ahead, please.
I have a quick question.
Yeah.
In GIMP or Photoshop, or even when you're programming in Python or something, basically you can pick any color you want and you're essentially layering them. If that's essentially what we're doing, then perhaps there could be like a basic red, green, blue, and then a more advanced one, because a lot of times there are different, more than 3 filters.
Yes, and that is the plan. And I think he may even have that in the version that's released in a couple weeks. I forget the technical term. I want to say merging, but it's not merging. It's almost like equations where you say, okay, my red channel is going to be this at the 50% level plus this at the 20% level plus that. And some of those could be narrowband filters. Some of them can be broadband. So like luminance, often these pretty picture sets are LRGB, where L is a broad filter. And I've never really understood how they incorporate them. other than there are these equations. So each layer has an alpha, which is basically the fraction of it that you want to put in the combination. I think it's just like a linear combination of different things. But yeah, that's the plan. And that may even be in the immediate version. Yeah, yeah. So I think students would get real excited once we give them this capability. And I think I will build a little bit of it into Lab 1, but we can't do too much because it does eat up time, right? You want to do this on Messier objects, which are longer exposures, and then they'll say, oh, I want to go deeper and want to do stacking, and then it violates the whole scalability model of this curriculum. This is the stuff we were hoping to build in that second multi-wavelength universe curriculum, and still will in time once we can fund it. Okay, some other updates. Lab 5 overview videos, I got those done. So that week off was helpful for me. I was able to catch up from the grant writing, and some of those overview videos were late, but I think I'm back to producing them just in the nick of time. So we have an introduction, background, and procedure video. And again, just basically walking through the lab. And if the students would read, then they'd get the same information. It's just another version of that. I was just talking to my TAs, and usually they don't read the lab. They just, you all know this, and they just try to start doing it. During normal semesters, we give them quizzes at the beginning to kind of ensure that they read the lab, but this is at least another way that they can get the information in overview video. So on to Lab 6. Let's see, I think I pulled it up here. So again, the instructions at the top, I'll update them once I have the overview videos for Lab 6, which I'll try to shoot this weekend. And then we do have the notice about putting observations in for Lab 7. And we had a little bit of a discussion about this as you were coming in, but just really quick, Lab 7 is the lab where they will make a Milky Way rotation curve, measure the mass of the Milky Way, touch on dark matter. We'll throw in the Magellanic Clouds so we can have a little bit of a dark matter discussion. And it's an important lab. It checks many boxes. It introduces spectroscopy, which they should have some exposure to, even in a survey sequence. Introduces the idea of Doppler shift, and that's really important before we get to Lab 8. Lab 8's cosmology, and cosmological redshift and Doppler shift are different. It's subtle, and it's often glossed over, though we try to emphasize that. And they won't understand the difference unless they've done some Doppler shift work. Normally spectroscopy in these introductory labs, they're looking at an emission lamp and measuring Balmer lines or something like that. So this is a very different approach. And I like that it's radio. I like that they get at least some exposure to something outside of the optical band. And of course, we can do the Doppler shifts here too. They learn about some other emission mechanisms like the H1 emission line. There's a lot of stuff in this lab. Anyway, a couple things. First of all, we're one iteration back with WebAssign on this lab. This summer, they iterated all the other labs except Lab 7. They were confused about one of the changes, and so it has gone through one less cycle of iteration. And currently, most of you still have the original version without the update using archival data. I do intend to push either this first iteration, which is okay. I went through it over the past couple of days, noticed kind of the same number of things that I've noticed in all the other labs after the first version. And I sent it back to WebAssign last night, asking them to make the changes by early next week. If they can, great. I'll push the second version out to you all. And that's the kind of level that's the version you've been working with all the other labs. Mostly it's things like paragraphs merged together, forgetting to do many of the hyperlinks, things that should have been bold that weren't bold. So it's less clear what's an instruction, what's not, things of that nature. You can, if I don't have the second version, I'll give you all the first version. I've already pushed the first version to UNC and to NC State, because NC State's doing this lab this week and UNC's doing it next week. And so if they're going to put their observations in this week, they need it. If anyone else is doing lab 7 next week, let me know and I'll push the version right now, and the current version right now. Otherwise, I'll wait and see if WebAssign can actually make those changes early next week and then push the better version. And then with all these labs, there'll be a version 3, but that's really cosmetic cleanup. Anyway, there's a description how to do this. There's a pretty good video I shot on how to put these observations in. I'll go through it next week. I just want to let you know that if you're approaching this, you will want your students to go and put those observations in on the 20 meter. And I'll talk more about this next week, but the current instructions say to do 1 second spectra, 12 of them at different places along the plane. And this usually works just fine, but sometimes it trips some kind of error on the Green Bank side, and the telescope goes into, it should go into an error state where everything would stop, the cue would be held, but it's not working, but it's not going into the error state. So then everybody else's observations go through and they get nothing back, and it's confusing. And they keep resubmitting and the same thing happens. They get nothing back until this unflagged error state's resolved. So we're trying to work with Green Bank. We're hoping they would fix the problem, but they declined to do that. But really, we just want them to put in that flag to catch it. Okay, we've gone into the bad state, hold the queue, stop putting observations through until they recycle the software. Hopefully we'll have that in place in the next week. If not, there are some hackish things we can do. But in the updates to the lab, I switched it to 2 second exposures. The Green Bank telescope backend updates like on a 1 second time scale. So I suspect if we go to 2 second exposures, we'll be good. So I feel I'm blathering or going in circles because many of you probably aren't going to do lab 7 this soon. But if you are, despite what the instructions say, I would do a 2 second exposure. It might be better. We're still trying to figure it out. But most of them go through. And if you enter that state, I just need to restart the software and then they'll put their observations in again. And they should get it. And it actually comes back pretty quick because it works day and night. And the data, you know, if the galactic plane is up, they'll get the data back within minutes, like all of it essentially.
I'm not understanding the timing problem because if you use those defaults, the defaults seem to always work.
Yeah, it seems to work like 95% of the time. And that's what we found this summer. And it could be something totally unrelated that was going on this summer that's fixed now. It's really, no one can reproduce the problem that we encounter it when hundreds or thousands of students do it at the same time. It's some subtle, probably a race condition, what programmers call a race condition, where you have competing processes going on simultaneously. And if they sync up in just the right way, it trips this thing. And so if you encounter these problems where students are submitting the observations and they're going through and then it's just a dead link that they're being pointed to, as you're doing lab 7, let me know. We're trying to troubleshoot this. The simple solution is just to do longer exposures. The question is how long. If it's too long, like if it's, Green Bank said we should do 30 second exposures. But if we did that, given all of our students, all of our institutions, and how big this is going to grow over the next couple of years, that would eat up all of UNC's telescope time on the 20 meter. And so I really want to make it work with 1 or 2 second exposures. Works most of the time. But if you encounter this problem like we did this summer, let me know. And just be aware that we're trying to fix it and troubleshoot it right now. Okay, so if there are no other questions or issues, jump into lab 6. Okay, so lab 6 is a natural follow-up for the previous lab. We've been doing the cosmic distance ladder. Lab 4 is parallax that got us so far out. Lab 5 is standard candles, where we used our Lyrae, Cepheids, and Type 1As to get farther, farther, and farther out. before going on, we're going to actually pause for the next two labs and use some of this stuff. And so in this lab, we're going to use the R-Lyraes and the Cepheids to redo the Great Debate of 1920. And this is a natural thing that you cover if you're doing a Stars Galaxies course, Stars Galaxies Cosmology, like an Astro 102, or if you're doing the whole universe in one semester, this is something you cover. And so it fits in really naturally with your lecture curriculum, which again was one of the goals of this lab sequence. Instead of doing things that you can do that may not match up with what you're teaching in lecture, trying to do things that really reinforce the lecture curriculum. Okay, so the three goals, we're going to use R-Lyraes in globular clusters to measure our distance from the center of the Milky Way. We're going to use them to measure the approximate size of the Milky Way. So we're going to use them as a proxy for the Milky Way. The Milky Way is full of dust. We can't see through it very easily. And so use the globular clusters, which are above and below the plane of the Milky Way. They kind of, their distribution is about the same size of the Milky Way. So if we use R-Lyraes in a whole bunch of them, we can map out that distribution. And then you'll see we'll do a top-down projection and figure out, are we at the center of the distribution or the outskirts? How big is the distribution? Gives us the size of the Milky Way and our place in it. And that's kind of the first half of the Great Debate. This is the part that Shapley was really big on. The second part of the Great Debate has to do with what they then called spiral nebulae, the little spiral, we know them to be galaxies now. We didn't know if the Milky Way was the primary object in the universe and these were just little things distributed around us, or if they are galaxies in their own right. So the students will image a handful of these and we'll give them information about Cepheids in them. And they'll use that to figure out the distance. They'll measure the angular size, calculate the physical size, and show that they're galaxies just like our own. So kind of two parts. Equipment, just internet. Let's see, we have three background sections, one on the Great Debate, a very simplified, boiled down version of the Great Debate. And then the two parts of it, the Milky Way part, and then the spiral nebulae part. The Great Debate, just brief summary between Harlow Shapley and Heber Curtis, left and right, 1920, held at the Smithsonian. And I'm no expert on the history. So this boiled down version is like straight from Wikipedia and introductory textbooks, and you may know more about it than I do. But from what I understand is they both kind of weren't, although it was a debate, they both were kind of making different points. Shapley was talking more about the size of the Milky Way and our place in it, and Curtis was talking more about the spiral nebulae. So, and they're both right about some things and wrong about some things. So let's start with the Milky Way. Curtis argued that we were at the center of the Milky Way, or close to it, and that the Milky Way was about 10 kiloparsecs across, which is small by about a factor of 3. It's about 30 kiloparsecs across. Shapley, on the other hand, argued that we are not at the center, we're in the outskirts. So he was right about that, but he said the Milky Way was huge, like 100 kiloparsecs across. So also off by a factor of 3. So they were both off on the size of the Milky Way by a factor of 3, but Shapley got our place in it correct. And again, in this lab, we'll use the R-Lyraes to figure it out. The second part of the debate was the Milky Way's place in the universe. And, Shapley said, our Milky Way is so big, it's got to be the primary thing in the universe. So all the little spirals we see out there, they just got to be little things distributed around us. Again, making the classic mistake that goes all the way back to Greek times, where we keep putting ourselves at the center of all things. Here we are in 1920, still doing the same mistake. Curtis putting us at the center of the Milky Way, Shapley putting the Milky Way at the center of the distribution. And again, the lab sequence is called Our Place in Space. We're using the cosmic distance ladder as the backbone, but this is our lesson. And it goes all the way out to lab 8, where we learned with Hubble's law that there is no center to the universe. Anyway, Curtis argued that The spiral nebulae are farther away, and if you calculate their physical size, they're not too different from the Milky Way's physical size. So we're just one of countless many similar objects out there. Okay. So first on the Milky Way in this globular cluster distribution, just a little background of what these things are for the students and how they're distributed. You know, if you have a large cloud of gas, and again, I know you know this stuff, but just presenting it as you might, you have a large cloud of gas. These large clouds are kind of borderline unstable. You disturb them just a little bit, they begin to collapse, but they don't collapse down to a single object. They may be like 100,000 times the mass of our sun. You don't get a star with 100,000 solar masses. As it collapses, it fragments, and the fragments fragment over and over until you have a cluster of stars, like this globular cluster. Now, if this happens in the plane of the Milky Way, these star clusters get torn apart by gravitational shear and all that. But if these formed up above the plane and below the plane, they're still there, nothing to really disturb them. So this slide kind of shows the formation of our galaxy, very cartoony, but you have a bunch of these gigantic clouds at this point merging, forming our galaxy, and eventually collapses down to a rotating disk. But as it was doing it, these star clusters formed and they entered orbits up in this vicinity. And although the gas collapsed down to form a disk, these ancient star clusters, globular clusters, are still there on highly disordered random orbits, but there's nothing out there to disturb them. So they've maintained their structure. And because of this, they're distributed over kind of the same scale as the galaxy as a whole. And again, it's hard to study the size of the galaxy because when we look into it, we just see dust and it blocks our view. But these are up above and below the plane, and so we have good views of them. So the idea is they all have our Lyrae stars, as the students saw in the previous lab. And we're not going to make them re-observe our Lyraes in each one, but we're going to give them a bunch of them. Not all, they're like 150. That's too many for the students to do. So we picked a subset of 30, and we give them the information about the R Lyrae, and they calculate the distance. And once they have the distance and the angular coordinates, they can make a top-down map, and we'll use our custom graphing tool to help them because that's some pretty tricky trigonometry and geometry. We make it real easy for them. And they'll get some distribution for the globular clusters, and they can find out where are we in this distribution? Are we at the center? Are we in the outskirts? And also how big is the distribution? That's the first part. Here's the other background section on the spiral nebulae, most famous one being Andromeda, but lots of them all over the sky. Are they tiny things, or are they things comparable in size to our galaxy? So for these, we give them Cepheids. Again, they're not going to observe it. They learned all about how to use the Cepheids last time. We're just going to give them the periods and the apparent magnitudes, average apparent magnitudes. And they'll calculate through the same equations they learned last time, the distance to these spiral galaxies. And then they'll calculate the physical size. And voila, here's our same geometry all over again that we've seen in labs 2 and 3 and 4, and now 6. I don't think we hit this geometry in lab 5. But the angular size they measure as a fraction of 360 is the physical size divided by 2 pi times the diameter away. We use this for parallax and all sorts of things. And so here it is solved for diameter. So once they know the distance from the Cepheids and measure the angular size from their image, then they can calculate the diameter. Okay, those are the background sections. Okay, so procedure. Let's look at, we have 3 procedure sections. The first is our place in the Milky Way and its size. And the last 2 are about the spiral nebulae, where one of them is putting in their observations. So we introduce them to galactic coordinates, where 0, 0 points to the center of the galaxy. So here's 0, 0, and galactic longitude runs along the plane. Galactic latitude runs perpendicular. So this is the coordinate system we'll be using. And then we've given them this random sample of 30, where we have longitude, latitude, apparent magnitude. We give them that. They're going to enter the absolute magnitude of the R Lyrae, of our Lyraes. which is the same for all our libraries. They should have learned this in the last lab. It's 0.75, and they calculate the distance. And we use this as an opportunity. This was not in the labs before, but we've built it in. And I'll probably make a little tweak to this as well. There's a tutorial on how to do this with a spreadsheet. And so they're going to learn some basic spreadsheet skills, which I think is just a valuable skill for them to have in general. So in the video, you know, they can calculate all these by hand with the calculator, but it's really cumbersome. So we tell them to highlight the table, Control C, and then go to a spreadsheet and paste it. And if you Control V, it pastes. You have a couple problems. And the video, and I didn't know about pasting as text. I didn't think about it. So in the video, I have them Control V, and then I show them how to get these logic boxes out of the way. They're really difficult. You can't just highlight and delete. They stick around. Also, in WebAssign, they didn't use negative signs. They used dashes. I tried to give them switch negative signs. They say, no, it doesn't look right. They use dashes. And so when we copy and paste this into the graphing tool, they're not recognized as numbers. And again, in the videos, I go through techniques for like copy and replace in the spreadsheet. But a simpler approach, or why I can't Control Z. Oh, Control V, sorry. No, Control Z should undo. It's these damn logic boxes. Okay, so let me just go to a fresh sheet. Instead, you can paste special as text, and then you lose all that, and all the dashes are turned into negative signs. You may just have to expand things a little bit. So I'm probably going to reshoot the video to do this. Expand it out here. Yeah, those logic boxes are just a nightmare in spreadsheets. Okay, and so for all our libraries, it's 0.75. I don't say this in the video. I kind of work my way around it. You can type it in, you grab that corner, pull it down, and then you have 0.75s everywhere. And then the logic for calculating the distance, again, they learned this last time. And in the video, I explained you got to use the equal sign. And so 0.01 times 1.585 to the parentheses, little m, which is this column, minus big M, which is that column, calculates the distance for them in kiloparsecs. Of course, I go through it a little bit slower in the video for their sake, in case they've never done anything in Excel. Show them how to copy the logic down. And then they can enter this stuff back into, pull that out of the way for a second, into here. Unfortunately, you can't paste back into here, so there will be some typing going on. But having that in Excel, you know, save them the calculation time, and it'll make it easy to graph it in just a second. Sample calculation, and then we're going to go to the graphing application, and we're going to go to scatter. And this takes the longitude and latitude and the distance they just calculated and does a top-down projection. We just have some junk data in here right now with the sun at 0, 0. And so we can grab the longitude and latitude data here. Paste that in, adds the extra columns if you need to. We had something like this in our old graphing application, but you couldn't cut and paste. Copy, paste, and voila, we have a top-down distribution without them having to do the 3D geometry. And, you know, they can put in labels, you know, maybe indicate kiloparsec and appropriate titles and everything. But you can see here, the center of the distribution, they kind of measured by eye, but it's around 8. So we're about 8 kiloparsecs from the center. And the size of the distribution, it's running from, I don't know, minus If you hover over that, like -7 or +23, so 30, 31, 32 across, or they can measure it this way. It's only 30 points, so you have to eyeball the center. And the human brain's really good at eyeballing the center of a distribution. We can usually get it to 3 to 5%. The outskirts, that's harder. It's really sparse out here. But these are the sources of error they'll talk about. And so they'll, finish that up with the labels and upload the graph here. And I'm not in answer key mode right now. And I'll stay out of answer key mode because I'm going to copy and paste some more of these tables in a second. But in answer key mode, you basically see the graph you were just looking at. Here they estimate the distance between us and the center. Then Google the true distance. It's about 8.1 kiloparsecs. Percent error, significant sources of error. Again, just eyeballing the center of that distribution. Then ties to the history. Who is more correct about the solar system's place in the Milky Way? Shapley, if they read the background section, he said we were in the outskirts. Curtis said we're at the center. And then the second part, how big is the Milky Way? Estimate the distance across the distribution. Look it up. Percent error, sources of error. Again, eyeballing the edges. It's kind of hard to do. And it's pretty generous in the auto grading, so you don't need to worry about that. Who's more correct about the size of the Milky Way, Shapley or Curtis? And it's neither. And I try to emphasize this in the videos. They may say Curtis because they think in terms of addition and subtraction. Curtis said 10, Shapley said 100, the answer is 30. So an astronomer says, yeah, they're both off by a factor of 3. So neither of them got it right. They may say, well, Curtis was only off by 20 and Shapley was off by 70. The answer is neither, but I tried to emphasize this in the videos. Maybe I should add some text here as well to think in terms of factors. Kind of thought I did. I should check and see if that's something they missed in the implementation. Anyway, that's the first part. Second part is Curtis's time to shine. But first they put in their observations. I picked 5 spiral nebulae. At least, we don't yet know they're galaxies, spiral nebulae. And they're going to observe in the high through filter 80 seconds. And these just kind of a random distribution. Some are a little bit bigger, some are a little bit smaller, and they're not all observable at any given time of the year. 3 or 4 of them tend to be. So they get as many as they can. And it's just basic observing. They've done this many times. Single shot, it's not a monitoring observation, it's not parallax. So this should be very easy for them to put the observation in. I don't even have a video walking them through this observation. They should know how to do this by now. Okay, and now we're going to determine distances and sizes of these spiral nebulae. So was the observation successful, yes or no? We haven't put this here. And again, we have one of these boxes, sign your name to attest the fact that you collect the data yourself. This is important because in this table, they're just going to calculate the absolute magnitude based. So we give them the apparent magnitude, we give them the period. They're going to calculate the absolute magnitude and the distance. And they could do that whether observed or not. And the idea is we're just going to give them credit for the observed ones. But they could still fill out the table. So the table will auto grade, but it's not worth anything. When you're doing manual grading, you'll go and give them their points here. Again, it's like lab 1. They could submit a whole bunch of junk for planets that were not observable. And so we kind of do auto checking, but you assign the number of points manually to make sure they're not cheating the system. Still not super happy with it, but I can't think of anything better yet. And they do a sample calculation for absolute magnitude and for distance. And again, we encourage them to use a spreadsheet. And this is actually described in the previous spreadsheet video. And I may split that and have a separate video here just for this. But let me show you how this works. Now, first of all, if I do paste, I just learned this an hour ago, if I paste this as text, it doesn't work because of those damn drop-down boxes. It doesn't come out with everything in the right column. So I may change those drop-down boxes. Otherwise, you could just paste normal, and I walk them through this procedure of, okay, these are kind of messed up, so I'm going to, in the video, this is how I tell them to deal with it. You insert a couple, copy, paste, and then you can ignore these columns over here. You can delete them, but it doesn't matter. So that's how I tell them to, before I knew about paste as text, this is how I was telling them to deal with it. And then it's the same deal. The magnitude of a Cepheid, I forget the equation, but it's in the previous lab. But if I go to show all, it'll be down in the answer key. It's like minus 1.43 minus 2.81 times log of the period. Let's find out. Yes, that's right. So you type in the logic. Minus 1.43 minus 2.81 times log of the period. You gotta make sure there's an equal sign before it. So you have that, and then the distance is again 0.01 times 1.858. I know that messes with everyone. You're used to 10 to the difference over 5, but they can get messed up there. So the apparent minus the absolute. Then grab the logic and drag it down. And these are the distances in kiloparsecs. And they'll enter that stuff in the table here. Yeah, it looks like I did it right. My numbers are matching what's in the spreadsheet. Let me put this over here for a second. So the honor code, sample calculation for the absolute magnitude, sample calculation for the distance. And now they're going to measure the angular sizes from their images, and they'll go in this table. I'm going to go out of answer key mode so I can copy that table. But while it's thinking about that, let's go back to Afterglow, and I'll show you how to here's Afterglow. This is not one of the ones in the table. I just grabbed a galaxy. And the instructions here are to change the saturation level to 90. I think that might be the faint, no, 95 is the faint target, to go all the way to 90. That helps to illuminate the outskirts of the galaxy. And then they go to the measuring tool, and with centroid clicks off, because we're not measuring from point to point, you go from one side to the other. And then you have the angular separation in arc minutes is what the table is going to ask for right here. Now, sometimes it may be a little bit half off the image, your galaxy, in which case you may not see one side. And the instructions tell them to measure from the center to the side they can see and double it. Again, the auto grading is really generous. And so it should work either way. So I'm going to grab this table. And there's so few of these, they could do it by hand if they wanted to. This one I can paste as text because it didn't have that weird yes, no box. Minutes, degrees. Okay, so here they're going to enter their measurement for the number of arc minutes. They have to convert to degrees, so that's going to be equal to this one divided by 60. And then they're going to calculate the diameter, which was their angular measurement in degrees divided by 360. This is in the background section, times 2 times pi, which is a little function there. And in the video, I tell them how to do that with the closed parenthesis times the distance away, which is right here. And, once they measure some size, this was a different galaxy, but I think I measured 7 arc minutes is the diameter. Then they get a physical diameter here. Again, they can copy the logic down, or these would be their various measurements. I'm just making stuff up here. And you get a distribution of sizes there. I'll go back to answer key mode. Hop on down. And you can see here we have 2 that are Milky Way size. Here we have a couple that are smaller, one that's bigger. They present their calculation for the angular diameter here, significant sources of error. Then we ask, how does the Milky Way have the size of the Milky Way compared to the size of the spiral nebulae in your random sample? Is the Milky Way many times larger than, many times smaller than, or typical of the spiral nebulae? And it should be typical, as you can see from the answers here. And who was more right about the Milky Way's place in the universe? In this case, it was Curtis. It's a pretty straightforward lab. It's the fastest of the labs. They can plow through this one pretty quickly. It builds directly on the previous one, so don't do lab 6 without lab 5. If you're picking and choosing labs, these two can go together very naturally. I think that's all I have. So I actually finished ahead of schedule today for a change, and I'll just stop and, for comments and questions and things. Anything? Well, if not, then next week we'll do lab 7. You may want to go and take those radio spectra for yourselves ahead of time. Again, there's a video that explains how to do it. It's pretty straightforward. And you get to start moving around our giant radio telescope, which if you haven't done that yet, that should be fun for you as well as for the students. And you'll have a data set for next time then. Okay. See you next week. We're almost done. 2 more weeks.
Thanks, Dan.
My pleasure.
you.
Gloria, did we get everything set up for your 2 students appropriately now?
Yes, and I'm sorry, this is the first day that I've used Zoom on an iPad. And
Oh.
the all the little icons are in a different place. So but yes, I think they're set up and ready to go now. I'm just really, if I had somebody to talk to about web assign, I think that would be good. Somebody who has time, not to set things up like I do. Just, I don't want to bother you with all those little questions.
No, it's okay. That's what I'm here for. Your first time through the sequence, I'm here to answer all the little questions. So don't worry, just email me or Zoom me and we'll figure out whatever you need.
Well, the main thing is getting them into those courses, because I had signed Colin up the same way, and he said that he had a problem and he had to do something else. So I was wondering, when I add them to the course, what happens then? I've added them in WebAssign.
Yeah, so I wasn't able to answer that one for you. The way I normally do it is I have them auto register. I give them the class key, and then they go to the front page of WebAssign. There's a button right in the upper right saying enter class key. And they do that, and they can create their own account in that section.
And then I can find the class key when I go to each section should have its own class key, right?
Yep, that's right. Each section you can go to edit class settings and see the class key. There's also another button saying view class key.
So do I take them out of the class? Do I now take the students out, give them the class key and tell them to?
I probably wouldn't mess with that. Since you've already added them, I think all that you have to do is let them know what email address you used, because they log in using their email address. So if they log in using their email address, they should see it. They may not know their password. That may have been the issue.
I set the password to be their same as their student number.
Okay, so if you give them those two pieces of information, they should be able to just log in.
And then they'll automatically see the course.
Yeah, now the issue may be the grace period is long over. When I set this up, I set it up with the start date for your semester, and there's a 2-week grace period where they can see stuff. So they may immediately be asked to pay before they can see anything.
And so they would need that, the code that my secretary is picking up.
Yep.
Okay,
that's right.
well, I'll send them the email once we get that code to make sure that they won't have a problem.
Until then, I made a PDF I opened up all the accordion tabs and made a PDF so they can start reading the background section and watching videos.
Yeah, that looked pretty good. I was actually kind of embarrassed that I hadn't thought about doing that myself because it
Okay.
looked as good as the guide PDF.
Yeah, and I will update all those once I'm done iterating with WebAssign and we get it kind of in a final state.
Okay. Well, pretty happy to see you and thanks for all of what you're doing.
Oh, my pleasure. I'm glad.
I don't want you to give them that radio assignment though, because I want them off that telescope.
you use that a lot, don't you?
I use it a lot, yeah.
Well, fortunately, if these exposures are only like a second or two, it's not going to eat up hardly any time. And if lots of students do it simultaneously, as we talked about before, if there are many observations in the queue that are identical at the top of the queue, we observe it once. So if whole classes put this in at the same time, it may only eat up 12 seconds. So hopefully we've done this well and we won't be eating up lots of radio time.
Okie dokie.
Okay. Talk to you later.
Thanks for everything. You might have to end this because I don't know how to even end from the iPad.
Yep, got it right now.